Hi, welcome to Thorlabs. My name is Matt, and today I'll be discussing how to write a Python script to control a Kinesis motor controller and a power meter. In this case, these will be used as part of a variable laser attenuator. For this demonstration, I have here a Class 2 collimated laser diode, a fixed linear polarizer, a half-wave plate in a motorized rotation mount connected to a K-Cube DC motor controller, a second fixed linear polarizer, and a power meter with sensor. To adjust the power of my laser beam, I could just use an input and output polarizer in front of the laser. Rotating the output polarizer while keeping the input polarizer fixed would provide a sinusoidal change in output power, but in this case the output polarization state would also rotate. Instead, keeping the output polarizer fixed and rotating the input polarizer would maintain the same linear polarization state at the output, but the power is not likely to be sinusoidal. Because I want a known sinusoidal change in output power with a fixed polarization state, I've added a half-wave plate in between the two polarizers. The first polarizer is aligned parallel to the input source, such that the power is maximized, and the output polarizer is aligned so that the throughput is minimized, and this creates a crossed pair of linear polarizers. Now, rotating the half-wave plate rotates the linear polarization state relative to the output polarizer, which provides a sinusoidal change in output power with a constant linear polarization state. Automating control of this variable attenuator requires characterizing the output power as a function of the waveplate's rotation angle. So let's take a look at one way to do that. For this application, we're using Python 3.10 and Visual Studio Code to write the program. The Kinesis libraries are developed using the .NET framework, so you should also go ahead and install PythonNet if you have not done so already. This can be done directly from pip. Here on the screen, I have a blank Python script open in Visual Studio Code. I have the time package imported at the top, and for this tutorial, I'm going to split up implementation of the devices to keep things clear as we build up the program. Starting with the K-Cube, I'll show full initialization, movement of this mount, and then shutdown, and then after this, I'll implement the power meter functionality. So let's start by importing PythonNet into the script. This package enables Python to interface with the .NET Common Language Runtime and is imported with the CLR designation. So at the top of the program, I'm going to add import CLR. And this allows us to use .NET namespaces as if they were normal Python packages. So let's import the classes we need for the motor controller. And since we're working with Thorlabs specific DLLs that are not included in the .NET runtime, we first need to add references to these with the addReference method from the CLR package. With the DLL references added, the namespaces within these libraries can now be added into our script. For this application, we'll need the Device Manager CLI, the Generic Motor CLI, along with the K-Cube motor class and the jog parameters base class, which are also found in the Generic Motor CLI. We'll need the K-Cube DC Servo CLI. And the Kinesis libraries also use the decimal type for setting move parameters and stage settings. So we'll import this from the system namespace. In our main method, we can begin adding the motor control code. I'm going to start off by creating a serial number variable. I'm going to be assigning this using the str constructor so Python knows to treat this as a string. To load available devices into memory, we're going to use the build device list method. This is from the Device Manager CLI. And then we can initialize a new variable for the K-Cube using the create K-Cube DC Servo method. I'm going to call this controller, and this takes the serial number as an input. Next, we want to check that this connect method did not fail. So let's set up an if statement to check if this controller is equal to the Python type none. In the if statement, we can start by calling the connect method on the controller. This also takes the serial number as an input. The program should then wait for the cube to finish connecting and loading any settings. And we'll use an if statement that checks if the isSettingsInitialize property returns false. And if it does, we'll use the waitForSettingsInitialize method to give it some time to finish up. The start polling method should then be called on the controller. This instructs the K-Cube to send updates about position and motor status to the PC, and the update rate for these values is specified by the input to the method in milliseconds, in this case 50. A 100 millisecond wait is added after this to allow the controller to update. And then we call the enable device method, followed by another 100 millisecond wait. The parameters for the rotation mount we're using now need to be loaded into the K-Cube. To do this, we first need to create a variable for the motor configuration. And then we'll change the device settings name property to the part number for this mount. The update current configuration method is then called, and then the set settings method from the controller is used to finalize these settings. This takes the motor device settings from the controller as an input, along with two booleans. The first boolean corresponds to if the settings from the controller are going to be currently updated, and the second is if they should be persisted to the controller. With the controller fully initialized, the rotation mount can then be homed. This method takes a timeout value in milliseconds corresponding to how long the method should wait before throwing an error. If the move completes before this timeout is elapsed, then the method will return and no error will be thrown. Let's also add a print here to help visualize the flow of the program. Before moving the motor, let's also set our velocity parameters. This new jogParams variable is set using the getJogParams method from the controller, and this just allows us to store the current state of these settings from the controller. Now let's go ahead and edit the step size property. For now, let's set this to 10 degrees, and this is going to be set as a .NET decimal type. Let's also set the max velocity to 10 degrees per second. And the jog mode of the controller can also be updated. This variable containing the updated parameters is now sent to the setJogParams method. The moveJog method is then used, and this takes the motor direction as an input along with the move timeout. Let's add another print statement in there. And once the move is finished, we can close the controller first by calling the stop polling method. And then the disconnect method. And now let's run the program to test the functionality. Here on the screen we can see our program started. And there's our print to indicate the home method started. And now our motor is moving. Now that we've confirmed that the rotation stage is implemented properly, let's move on to the power meter. If we then wanted to add power meter functionality into the program, we can start by copying over the TLPM Python library and the TLPM DLL into the folder containing our script. This is an official library developed by Thorlabs for the power meters, and this uses the ctypes package to pull in the functions from the DLL. Once copied, we can import the library like any other Python package. And because this uses the ctypes package, we'll also need to import some data types from this. Depending on your development environment, you may also need to instruct the program to search the current working directory for the DLL when loading in the TLPM library. In our case, this is needed, so we'll go ahead and import the OS module. And in the main body of the program, we're going to use the add DLL directory method to set the path. As an input to this method, we're going to use the get current working directory method that's also from the OS package. To initialize the power meter, we first want to initialize an empty TLPM variable. And this is going to allow us to find any connected power meters. Returns from the methods in the TLPM library are passed by reference. So, before calling the findResources method to return the number of connected devices on the system, we first want to initialize an empty variable as a cuint32 type. This variable allows us to call the findResources method, and this is going to return the number of connected power meters on the system. Next, we want an if statement to check if the number of connected devices on the system is equal to 0. And if it is, we'll print that to the console and quit the program. Next, we can get the connection string of our meter with the getResourceName method. For this, we'll need a string buffer to pass by reference, so let's create a variable called resourceName. And then we'll assign this using the getResourceName method. This takes an integer corresponding to the index of the power meter to be connected, and the resource name. The meter is then connected using the open method, which takes the resource string and two C booleans. And the last thing we need to do before taking measurements is to set the current operating wavelength for the power meter. This is done using the setWavelength method, and this takes a C double type for the wavelength. A common use case for the power meter is to continuously monitor the power of a source. In our case with the variable attenuator, the power would be changing rapidly while the motor is moving. However, the jog method is a blocking call and does not allow us to check the power at the same time the motor is moving. To get around this, we'll instead set the jog timeout to be 0. This will cause the move method to return immediately without checking if the move was actually completed. A wait is added after the move method to allow the status of the controller to update. And then we can add in a while loop that will only run while the motor is moving. The condition of the while loop that we want to check is that the isDeviceBusy property of the controller returns true. As long as this is true, it means the motor is moving, and while it's moving, we want to continuously monitor the position and the power. In the while loop, we'll start by initializing an empty C double variable that we'll call power, and this is needed to pass as reference to the measure power method of the power meter. So let's go ahead and call that measure power method. And once that's returned, we can print the position of the rotation mount along with the power to the console. The power returned by the meter is defaulted in watts, so we can multiply this by 1,000 if we want to display the power in milliwatts. A delay then needs to be added to the while loop to control how often the power is measured. Since we're rotating at 10 degrees per second, we'll enter a wait time of 100 milliseconds to provide a power measurement approximately every 1 degree. Now we also want to go back and update the jog distance that we set previously. For our variable attenuator, we can reliably fit the data to a sinusoidal function if we rotate the motor by 180 degrees. And finally, to disconnect the meter at the end of the program, we can use the close method. And now let's test the code. On the screen here, we can see that the program is started. Now we see our home method is started. And we can see the move indicator is printed and our power measurements and positions are printed to the console. Now that we've created a lookup table that relates the output power to the half-wave plate's rotation angle, we can fit the data and create a function that finds the angle given a desired output power. I hope this helps you in the lab someday. If you have any questions, please contact tech support.